Hi guys, this is our lecture on conservation of momentum and collisions. This is part 1 of 2. Let's get started. So we're going to be talking about car collisions over the next couple of weeks, but in order to have a good understanding of car collisions, we need to have a more basic concept, which is the conservation of momentum law. And the law of conservation of momentum states that in the absence of external forces on the system, the momentum remains unchanged. And so as a quick example of that, if we think about a cannon shooting a cannonball, the momentum before firing a cannonball adds up to 0. Right? If we say that the momentum of the cannon, well, that's at rest, that's 0. And the ball itself is not moving, so that's 0. Okay, so we've established that before we shoot a cannonball, the momentum of the cannon and the cannonball is 0. Here's where it gets a little bit more, or a little bit less intuitive. After firing the cannon, the net momentum, is still 0, because the momentum of the cannon is equal and opposite to the momentum of the cannonball. And you're like, what? How can that be? Well, our cannonball is moving to the right, and through Newton's third law, our reactionary force is pushing the cannon itself to the left. And so say we have 10 kilograms meters per second of momentum to the right. Our cannonball is going to experience negative 10 kilograms meters per second. And those will add up to 0. And so how is it possible that we've managed to get the momentum to be the same before and after? Because if you were to look at just the momentum of the ball, it'd be pretty clear that the ball's momentum is in fact changing. Well, it depends on how you define your system of study. And how you define your system of study will determine whether your forces are internal and can't apply a change of momentum, can apply an impulse on the system, or if your forces are external and can apply an impulse causing a change of momentum on the system. All right, so here we go. How do we determine whether or not a force is internal or external? Let's just do some practice. Here we have a system of study being a baseball only, and it's been hit by a bat. Well, in this case, the force on the baseball is external. Here we have our system as the bat and the ball. Well, the force of the hit is applied by the bat on the ball, and so we have a reactionary force. And so this force right here is going to be internal. It's canceled out by its reactionary force, and it's not going to change the overall momentum of the system. Here's a different one. We have a whale that's falling towards the earth. If our system is just the whale itself, then you're like, yeah, as it falls towards the earth, its momentum is going to change. It's picking up speed for a whale. So is this force of gravity internal or external to the whale system? Hopefully you think it's external, right? And we see the evidence of that in the sense that it applies an impulse on the whale, causing it to change its momentum, force times time. All right, what about now, if we change our system to include the whale and the earth, is the force of gravity on the whale internal or external to the system? It's internal, right? And we can see that because if the whale has a force of gravity on it, the earth has a force of gravity on it as well. And the sum of the momentums is going to add up to 0. Why? Because these internal forces are going to cancel each other out. But as the whale moves down more, the earth's going to move up more. Okay. Here are 2 practice problems. Right? We'll let you attempt them. Go ahead and attempt them now. Right, on the left, we have an external force. Here we have an internal force. Over here, we have internal forces. And over here, we have external forces. And so is momentum conserved in each of these scenarios? Well, here it's conserved. Here it's not. Here it's conserved. Here it's not. When we have external forces, momentum is not conserved. All right, and so a common example of the law of conservation of momentum is Newton's cradle. Newton's cradle, we can see the momentum before and after every collision is the same. If I send 1 ball's worth of momentum into our cradle, I'm going to get 1 ball out. Okay, let's take a look at that in video form. So Newton's cradle is an excellent example of collisions. Collisions show the law of conservation of momentum pretty clearly. And this gives us a pretty powerful tool because momentum is, remember, mass times velocity. And so if momentum before and after collision are equal, that gives us the following equation: m1v1 plus m2v2 equals m1v1 final plus m2v2 final should be 2. Right? And if we know the majority of these velocities, then we can say determine the direction of motion and speed of motion of objects after a collision. We have two main types of collision. Elastic are collisions in which objects will collide and move off separately afterwards. Inelastic are objects collide and move off together afterwards. But in both cases, momentum before and momentum after are the same. Okay, let's take a look at a quick video of the difference between elastic and inelastic collisions. All right, so what we saw was different hot wheels colliding. Elastic collisions, again, objects collide and move separately. Inelastic collisions, objects collide and stick together. Good example of inelastic: trains coupling, moving off together, bullet being shot into a block of wood. To summarize, momentum is conserved when we have no external forces on the system, nothing to apply an impulse. External forces are defined by how we look at our system that we're trying to study. And then finally, we have two types of collisions: elastic collisions, where objects hit each other and travel separately, and inelastic collisions, where they hit each other and move together afterwards. In both cases, momentum before and after a collision is 0 because we consider all of the objects moving at the same time, and our forces are therefore internal. We can't apply an impulse on our system. That's it for now.